here we are. We have initially found out the initial basic feasible solution, which is known as IBFF. And the methodology we followed is the row minimum method, and matrix minimum method, and northwest corner method, and Vogel's approximation method. Right? Among these methods, Vogel's approximation method produces an optimal solution, or actually the most least cost or initial basic feasible solution. Right? So that's it. A quick recap, like before we get into the other methodologies. First, we talked about the row minimum method, in which we take a particular row and find out the minimum transportation cost in that particular row. We'll select that particular cell and we start allocating it, and finally we'll end up with the allocations of all the supply and demands, right? So that's what we call allocations. Then we talked about matrix minimum method. Instead of taking a row wise least transportation cost, we take the matrix wise. So we consider the entire thing as a matrix and find out minimum of these cells or among these cells which has the least transportation cost. We select that, and then we try allocating based on the lesser increasing order of the lesser transportation cost. Right? Then we talked about northwest corner method, when which we focused on the northwest orientation. Then we start allocating it, and finally we got the allocations. And then we stepped into VAM, Vogel's approximation method. We introduced one column as well as one row. The column is called row penalty, and the row wise is called column penalty. And we select allocations based on the number of penalties, I mean the value of the penalty which is higher. And then if, for example, in this case 280 is higher, so we select column, this particular column, and we start allocating into the minimum, wherein in this case you can see the row has had higher penalty, so we select this particular row and we allocated in the least a cell that has a least transportation cost or something like that. And finally we end up with this allocation, right? And if you note that the number of allocations matters the most, right? So number of positive allocations, we have varied allocations, like the cells may not be same. For example, if you see the row minima, the allocation is like this, the allocations is like this, and this. If you count number of allocations like 1, 2, 3, 4, 5 and 6, let's take a look at the matrix minima. In matrix minima, the number of allocation, you see the pattern is different, but the number of allocations is the same, right? 1, 2, 3, 4, 5 and 6, right? So even in northwest corner we have got 1, 2, 3, 4, 5, 6, and VAM also we have got 1, 2, 3, 4, 5, 6, right? So there is a check, actually it's actually a formula. It's called n plus m minus 1, right? So n is the number of source, which is 3 in this case, and m is the number of destination, which is this 4 here, right? So 3 plus 4 is 7 minus 1, so that is 6. So the optimal allocation, this is called optimal allocation. In this case, luckily we have got all the allocations to be optimally allocated, not the value but allocated, right? Some case you might have some method will yield only less than the optimal allocation. Say if it is 5 or 4, 7 may not be possible because it will be always less than the optimal allocation, right? So in that case you can discard that particular method. So that's basically the one I want to tell you. So it's actually a theorem which says that for a transportation problem to have an optimal solution, it should have n plus m minus 1 allocations. So that's simple as that. So it should have this optimal allocation. Then only there's a point in checking for optimal value, right? Say for example, if we have 5, if this method is 5, then taking that method and putting into the stepping stone method or Modi method may not be a wise idea, right? So since in this case all the methods yields almost optimal allocation, right? So exactly 6, which is the optimal allocation, then we can really get into the we can really get into the a perfect allocation or something like that, right? So that's basically that we want to emphasize, right? So far we talked about the initial basic feasible solution. Now we'll be looking into the optimal solution, right? So there are two methods. You can choose any one. Both yields the same value, so you don't have to really worry about that. And let's dive in about the optimal method to find optimal transportation allocation or transportation cost or something like that, right? The first method is called stepping stone method, and it's one of the complex method to understand, but it has its own significance. Whereas the other method we're going to try is MODI or modified distribution method, or it's also known as UV method. So it's a little easy when compared to stepping stone method, but stepping stone method will provide an insight of what happens in your transportation table, right? So without a further ado, let's get started, right? So we have got the transportation table. It's a balanced transportation problem. Sum of rows, sum of supply is equals to sum of demand, or sum of row sum equals to sum of column sum. Right. Now what we're gonna do is this red color unallocated cell, right? So we're gonna name that, right? Since we use Aij and Bj and Cij for nomenclature, so we'll start with the D, right? So we'll start. We can even start with ABCD, so that's not a very no wrong method or something, but it's just a nomenclature. So I've just put name the unallocated cell. So here is unallocated cell, which means we have not put any allocations, right? So we name them as D, and the another allocation is E. So you can take that as row wise, then you can come back to this F, G. So it doesn't matter, you can name any way also, right? So finally what we're gonna do is we're gonna try allocating this unallocated cell and try to see if this produces more optimal or overall lesser transportation cost when compared to the previous method or the initial basic feasible solution, right? So that's our basic logic. So we put D here, then we try putting it E, then F and G, then H, which is this unallocated cell, and finally I, right? So 1, 2, 3, 4, 5, 6. So there are 6 unallocated cell, and we're going to try to achieve the what could be the value for that particular what could have been an allocation for that thing, so that the overall transportation cost is minimum. So that's the basic objective of finding this particular nomenclating this particular unallocated cell, right? So let's take a look at the D, right? So now kindly pay attention. This might be very confusing for some people it will be intimidating, or it was something like very complex or perplexing. So kindly take a look at it. So the first objective or first step we're going to do is allocate cell, allocate some quantities to the unallocated cell. So in this case we have taken D, right? So D is this unallocated cell, right? So it should form a closed loop, right? So you have to select such a way that this D should be put in with a closed loop of other allocations, right? I repeat, so D should be put in a loop. First we'll be drawing a loop around the D, which is unallocated cell, which comprises of the unallocated cell, and all the other elements in the loop should be allocated. So as simple as that, right? So in this case what we're going to try to do is we're going to try to start with D. Then if you try clicking this selecting this, and this does not forms any closed loop, right? So it will be a hanging loop, or it is not even a loop, it is hanging thing, right? So we cannot close this, start with D, end with D. So if you take this, you cannot take this, but you can try the other way around also, the anti-clockwise also, but generally it is clockwise is preferred. Say D, If you try doing by this way, then you cannot come back because there's an unallocated cell. So you will be having a trouble, right? So what we do is we take D, then we go to this 90, then we take this 110, then 170, and finally we'll end up at D. So you can take a look at this. We'll start with D, then we'll go to this 90, which is allocated cell, and we'll go to this particular 110, which is also an allocation, and we'll go up with 170, and finally we'll end up with D. So it's a closed loop, right? So you can take a look at this closed loop, right? Now what we're gonna do is we're gonna try putting some value here. So first we will be putting it a single unity. So one, if I substitute one, uh, it's a supply, right? So from a ginning factory to spinning mill 3, if I put 1 unit, right? So if I put 1 unit, so this will become 501, right? So the reason is that 330 plus 170 is 500. Then when I add a supply, when I add a supply, this should be 501, and the demand is also 111. So it gets increased, right? So that's not actually we try to achieve. So how do we go about and eliminate that is when we add 1 here, we can subtract 1 here. Say when I add 1 here, I can subtract 1. So which means the demand is in equilibrium. So here it is 89 and here it is 1 and plus 20. So it will be almost exactly 110, right? Something like that. But the supply is still increased here. So by 1 unit. But when you take a look at the supply of this thing, say 200, when I reduce 1, so this will become 110 plus 89, which is nothing but 199, right? So that's pretty much an different thing. So what we're gonna do is we're gonna add 1 to this, so that this will become 111, then this will become 89, then that will become 200. Say that's a very interesting thing, right? So but then if you take a look at this now, this will become 281. The reason is that this will be 111 and 170, that will become 281, but it's still 500 is there, right? So then what we do is we minus 1 here, so that this will become 189, and finally this will become 500, and this everything will be in equilibrium, right? So I'll explain that with this thing. Say initially it is 170, right? And we have got D here, and we have got 110, and finally it is 90, right? So what we're going to try to achieve that is let me spill this, right? So this is the thing, right? So initially the demand is 500, and the supply here is 200, and both the supply and it's the demand, which is the bottom thing, which is 280 and 110, right? So 110, right? So this is the initial thing. We have not done anything. Say if I want to increase 1 unit, say if I want to increase 1 unit, this will become 501, right? So that's an increase in supply. Then what we do is we'll this also increases by 1 uh, unit, right? So because of this, this gets also increased and this gets also increased, but this doesn't make any difference, and this also does not make any difference, right? Then we'll go back to this. So since it is it is 89, right? Say I add, that will become 89. So then this comes back to 110. But then the supply gets reduces to 1, so it will become 199, right? And now what we're gonna do is we're gonna add 1 to it. So plus 1 minus 1 plus 1 minus 1. So we'll add, if I add 1 to it, this comes back to the equilibrium, so 200, but this gets increased by 1 unit, so 281, right? Then we'll minus 1 here. So this will become 169. So that this will become 180 and the supply reduces to 500. Means that we have not changed the requirements, but then we have tried to change this particular stuff, right? So that's basically the closed loop gets formed, and finally we'll have got this particular value, right? So that's how we add 1, then minus 1, add 1, minus 1, and this is a closed or equilibrium, right? Now what we're going to do is we'll start with this particular allocation, right? So 720, which is 720, is a positive 720, right? Then it's a negative 480, minus 480, right? Plus 320, then minus 360. So the net change, or you can even see the value of D. The value of D based on this loop is 200, right? So if I try putting an allocation here of 200, and that will be the result of this loop, right? So unfortunately, this may not be an applicable, because if you have a 0 here or negative value, then that might be really have some valid meaning, right? So that has a valid meaning. Otherwise it's not gonna be useful, so we'll discard this. So the unallocation, the value allocated to this unallocated cell is 200, and since it's not 0 as well as negative, so we'll discard this, and we'll go about and find the value of E. What happens if we allocate to this particular cell, which is the unallocated cell called E, right? So we need to form a closed loop. Like, how do we form a closed loop here? Is that if I come back to this here, and if I come back to this here, there's no top value to have a loop here. Say I'll start here, I can end here, I can end here, and I can end here, and I can go here, and I can make a loop, right? So this is how it says. It can have any number of allocations, but it should form a closed loop. I cannot form a loop like E, this cell, then this cell, this cell, this cell, and this. Like, it will not go like this diagonal, but instead it could go only horizontal and vertical, right? It's as simple as that. Then this cell, and you cannot go back to this because it does not form a closed loop, right? So we talk about this, and I'll go here, then we'll go here, then we'll go down, and we'll go up, and we'll go the right, left, and we'll go up, and then we'll finish here itself. So it forms a closed loop. And more importantly, the addition and minus should be in equilibrium. Like, so for example, if I add 1 here, I'll minus 1 here. If I minus 1 here, I'll add 1 here. If I add 1 here, I'll subtract 1 here. When I subtract 1 here, and I'll add 1 here, and I add 1 here, I'll subtract 1 here. And if you see minus and plus, this will become equilibrium. And column wise, minus and plus, and row wise also minus and plus, and minus and plus. So it will be in equilibrium. So it forms a closed loop, right? So when you do it, like, this will be 800, which is the
Excuse
transportation
me,
cost.
sir.
Yeah,
Sir, could you just explain again why didn't you consider D, sir, the previous one?
which is having a value which is, as I told you, it is positive. So we need to find a value which is kind of a minimum. It will be negative or 0. So that's why we have not taken it, like, sometimes. Understand?
Okay, sir.
Say for example, if you add 200 here, so this will be an allocation here, right? So this will become 330 here, then plus 169 plus 200. It will be 699. So the supply itself is only 500. So that will yield us, it's actually the deficit, like 199 units cannot be supplied to here, right? So that's why. But if it is 0, right? So if it is 0, then probably it can have this 500 supply, which is this row will be in equilibrium, or sometimes it will be negative 20. So which means that we can probably allocate some 20 units to the other cell or something like that. So as simple as that. Say the maximum supply itself is 500 and the existing is like 330, plus 169, right? Say that's one unit. So this is where we will have the value of D. So if the value of D is thing, then this minus the sum of these two has meaning, whereas if D is 200, and this will become negative. So that's not possible. Like we cannot provide more than intended supply, right? But if it is one unit, as in this case, or it could be 0 units, this is if it's we'll take 170 itself. If you have 170 plus 330, then if you add 0 or negative 20, then we can provide some 20 supply to here, like so. That's in the cards and we can proceed, right? So I'll explain that, do not worry about that. So we will first finish with E, which is the closed loop here. We'll start with the E here, then we'll end up with this loop, and finally we'll go back to this 20, then 90 and 110 and 170, right? So we take this particular stuff, and 800, then minus 200 plus 280, minus 480 plus 320 and minus 360, right? So we have got 360, and also the rule is the same, like we didn't have a negative or a 0, so this is not a place where it can be allocated or something like that, right? Next, once we finish D and E, we can look into F, right? So F is here. You can F is little tricky, so kindly pay attention. If you take a look at this F, you might not see any loop at all, right? For example, if it go here, and if it go here, you cannot have a diagonal like this, and you cannot come to this thing, and it does not forms a closed loop. So it seems like that, right? Or if you take F here, goes here and here, and from here, and it does not seems like a closed loop. So but there's actually a loop that is pretty much a different, if you think it in a different way, you'll get it a loop. So the loop is that we'll start with F, then it'll go to this particular allocation, then you'll come back to the down stuff, then go to the left and go above, and finally you go to the left, and finally it forms a closed loop, right? Something like that. Positive value, then a negative value, then a positive value, then a negative value, then a positive value, then a negative value, and finally a positive value. So it's all in equilibrium, right? So when you try allocating it, it will be like 960 minus 280. Here is the value 280, then plus 480. It's a cumulative difference, right? Plus 480. Then minus 320, plus 360. Then it will become minus 600 plus 960 we have taken, so it will become minus 600 only. It will become 600. So the rule is the same, right? The negative, we didn't have anything called negative or 0. So which means if you provide that particular value, that will alter the supply and demand, and we will not get any perfect solution at all, right? So this is how it forms. Stepping stone, you probably know that game, no? Stepping stone, it will make allocation and see if it is optimum or something like that. So that's what basically the stepping stone is all about, right? And then this is the another allocation called G, when which G is fairly simple. It forms a closed loop in nearby, like 1, then it will become -1, then it will become +1, and this will become -1. And when you take a look at this G, it will be 240 minus 280 plus 480 minus 320, right? So minus 320. So as simple as. So this is also not a negative number or a zero. We actually need a negative number or a zero, so that we can go back to the other step. This is first initial screening. So once we have got zero or a negative, then that is where we can positively allocate, so that the overall transportation cost is minimum than the initial basic feasible solution, right? So if you provide any of these values here instead of that, then it will not fetch you an optimal solution. You can check that also probably after this class. Then the other allocation, I think it's H, no, H here. So H also can be a closed loop. So H, then -1, +1, -1, and +1. So it forms a loop. Say this will become 880 minus 600 plus 360 minus 320. Say this is 320, right? So it's also we are looking for a negative or zero, and what we get is 320, which is a positive value, and hence we have to look into the other allocated cell, right? Another allocation, you can take a look at this pretty close, which means that this particular cell G, so it forms a closed loop here. So 90, then 20, and 280. So this will become positive, this will become negative, and this will become positive, and this will become negative, right? So it's a closed loop here, right? And then when we take a look at this, this will become 400 minus 480 plus 280 minus 200. So this will become 0, right? So which means we have tried to achieve our objective. Since a negative numbers gives us more optimal solution, but since it is 0, there's no gain. In fact, this technically it's called no gain. Even you alter this, and finally you don't have, you will check whether you have some lesser value, the total transportation cost. Otherwise there's no change here. So that's basically the no gain, right? Sometimes you might get negative value, so that case is pretty much a very useful iteration, right? So maybe another example, we can take a look at the negative valued stuff. For this case we have got only 0, and we had checked almost everything starting from D, E, F, G, H, and this is actually I guess. So it should be I. Yeah, it should be I, not G. Yeah, it's I. So we talked about everything, and finally, what you can do is, like, you see the value we got, no? So the values like 360 and something like that, right? So here is 0. So we'll be looking into the particular unallocations here, right? So what we're gonna try to achieve is, once we know transportation table has become a 0 or a negative value, that transportation table is more of an optimal thing. So you can use a single table in your practice, and you can use pencils to make this loops, and you can erase that, something like that, right? So finally we'll found out this to be having some validation, either 0 or negative is what our objective to find out. We had just got a 0, so this table, and also we have checked all the parameters, like starting from D, E, F, G, H, and I, right? So all the parameters, none of that yields a negative value or a 0 except I. So we'll take that particular thing, right? So that particular loop is retained. Then instead of 1, we will make with plus x. X is a quantity that we need to supply, like, so 20 plus x, and 280 minus x, and 90 minus x, and this particular I, which is nothing but just an x, right? So for the clarity I remove I. It is just an x, right? Something like that, right? So now what our objective is to make this any of these to become 0, right? So to make any of this to become 0 and make sure that it is other elements are positive and not negative. So that's a basic idea. I repeat. So the reason is that I can provide x to be 1, 2, 3, and it goes on and on. So I can provide any positive number in x such a way that one of this cell will become 0 and the other one will become positive. So that's an iterative process. So that's the algorithm works like the stepping stone algorithm. So we're gonna try to do that. But if you take a look at that, so in a quicker sense, you can have two negative. We have two negatives, which is called 90 minus x, right? And then 280 minus x, right? So there's a two things there. So we can make easily one to become 0, right? So x cannot be a negative number, so we cannot provide minus 20 here because that's not in the cards. It's a positive number, so we provide x to be a positive number among this cell and we'll make 1 to be 0. Say for example, if I take x to, if I wanted to make this to be 0, I'll put 90 minus positive 90, which is 0, right? What happens if I try putting this 280 minus x to be 0 is that if I put 280 minus 280, it will yield me 0. But if I provide 90 minus 280, it will be negative value. So it's just not wanna provide. So I cannot transport a negative 190 bale. This is a cotton example, no? So bales of cotton that's supplied and demanded. It can't be negative. So this is ruled out. So that's why we generally look into 90 minus 90. And this could be 280 minus 90, right? So which means that we have got an allocation such a way that this will become x will become 90, right? So we know that x is 90. Then when we provide 20 plus 90, this will become 110, and 280 minus 90 is 180, and this is x row 90, and then 90 minus x is 0, so which means this is an modified thing, right? Now we can take a look at this allocation. This is what we got it from BAM. And then let's take a look at whether it is an improved oscillation or something like that. Say, for example, we've got the 600 divided by 330 plus 360 multiplied by 170, 320 multiplied by 110, and 280 multiplied by 110 plus 200 multiplied by 190 plus 480 into 0, which is no, not allocated, almost not an allocation, because if I allocate, if I include that, then it will become 1, 2, 3, 4, 5, 6, and 7 allocation, which is not possible, right? So we'll discard this. It's almost unallocated. Then 400 into 90, then that will become 3,99,200. So which means that we almost got the value from VAM itself. So which means that we don't say that we have got an optimal solution than VAM. So VAM itself has provided us an optimal basic feasible solution, which means that the initial basic feasible solution obtained using VAM is the optimal solution, right? So in this case, sometimes there might be a case where you get a lesser value, right? So we will be taking a look at that also in a subsequent lectures. But as of now, this is the stepping stone method, and this is having a process of finding out the loop and finally this is the final allocation, right? So I think this is the other way around. It is 90. This is after let me do this. Let me do this particular thing. So this is how we got it after the stepping stone method, right? So this will become 0 and 480, whereas, but this is in equilibrium. So 110 plus 90 is 200 and 280, something like that. So, oh, right. So this is 190 and this will become 110. So this is out of stepping stone method, right? So let's compare that with VAM. I'll just copy the final allocations. So this is what we get it from stepping stone method, and if you see, this is what we get it from BAM. But both has the same value, same total cost. You allocate 90 units of 400 or 90 units of 480 and 110 units into 320, and this is instead of 280 of 110 units, you provide 20 units there, and this instead of 190 you make it 280. So this is how it is allocated, right? Something like that. In this case, luckily we have got the both the values to be the same, right? So this is from by stepping stone method and this is from VAM, and you can directly conclude that whatever we have achieved in VAM itself is optimal. Even the initial basic feasible solution in BAM itself is optimal, right? So that's basically the stepping stone method, right? Next, we'll get into the modified distribution method, which is a very straightforward method. We don't have to really worry about a lot of things like forming a loop or something like that. So in an exam, unless otherwise stepping stone method is asked explicitly, you can use modified distribution method for finding out optimal solution for a transportation problem, right? So let's take a look at how it is. Like we'll copy the final solution from BAM. The reason we choose VAM is like our initial basic feasible solution in VAM itself is more of a less transportation cost when compared to the other method, right? So anything that is kind of an equivalent to an optimal, if you take and optimize it further, then that will become valiant, or that solution will become more appropriate than a solution which have got a lot of errors. Like if you take row minima method and if you substitute in stepping stone method, you may not get more accurate value than when you take VAM for your stepping stone method or modified distribution method, right? So let's take a look at that, the modified distribution method, which is this particular cell. And what we try to do is we try to nomenclature the unallocated cell, like in the previous case itself, like T, E, F, G, H, and I. Then what we do is we'll be putting extra elements like the V and U. So this method is also known as UV method. Like the row wise, you put U, U1, U2, U3. This is the nomenclature for rows, and columns we put V1, V2, V3, and V4. So the rest of the things is the same, right? And then the first and foremost important step in this is we will put u1 equals to 0. So before we say that, use for the rows, number of rows, so number of supply or sources. Say I ranges from 1, 2, 3. So this is ui. You can call this as ui. And this entire chunk is called vj. Again, it's called vj, right? So the entire chunk is vj, and j ranges from 1 to 4. So we have a 4 demand area or a destination, like v1, v2, v3, and v4, right? So u is 3, I equals to 1 to 3, j equals to 1 to 4, and final is that, right? Now what you have to do is initially you have to provide a 0 value for u1. So this is a very, very important assumption. You will provide u1 equals to 0. So once you provide u1 equals to 0, so this is a Cij. So all the transportation cost here, it is called Cij, coefficient value in the objective function, right? So all these things are Cij, and these are ui values, and these are vj values. So the formula, when you know one value, say if you know u value, you can find v, or if you know v value, you can find u. So using a formula called Cij, uij plus vij equals to Cij. Do you understand? I repeat, uij plus vij equals to Cij, or Cij equals to uij plus vij. So here it is. Cij equals to Uij plus Vij. And if you know any one of this, you can subtract from Cij to find the other. Say for example, if you know U2, you can subtract that from 960 so that you can find V1, right? And similarly, if you know V3, if you want to know U2, so you can subtract 280 minus this value so that you can find U2. So as simple as that. So this is how the value works, right? So you remember the loops, right? So what this formula tells you is that it is imaginarily forming a loop and providing a solution in this unallocated cell. So you don't have to form any loop at all. You don't have to really worry about whether the loop was correct or not. It will provide the solution as equivalent to a stepping stone method, right? Say when I initially put u1 equals to 0, so 600 minus 0 is 600. So the value of v1 equals to 600. Now we have got the value of v1. Now we can find out u2. So 960 minus 600 will be the value of u2. So once you find out that, you'll fill all the u values and all the v values. So first we'll try to finish row wise. Say this will be pretty easy. 600 minus 0 is 600. Then 360 minus 0 is 360. And 720 minus 0 is 720. 800 minus 0 is 800. So that's how we fill the values or something like that, right? And then since it's a single allocation, we can go about and do that. But in this case, we have got two allocations here, right? Something like two allocations. So which means that we can take 360. Then when we minus 320, we can get U3 value. Say, I'll just repeat. So first we'll try to do one by one. First is 600 minus 0 600. So once we provide that, and there's no other term to be calculated, so we'll leave that. Then we'll come back to this allocated cell, which is 360, and there's a 0, so which means 360 minus 0 is 360. We provide here, and then we have got another allocation called 320. So we know V2, we can find U3. So which means that if I minus 320 minus this 360, that will become minus 40. So remember, you'll get minus values also. So incorporate minus 40 here. So that's how we got minus 40. And once we got minus 40, then we look into the other cell, because this allocated we have found out, and here it is. And this is how we found out here, right? Something like that. Say 320 minus of minus 40 is 360. So which means it's in equilibrium, right? So that's how mathematics will take care of by itself. Like then we'll come back to this allocated cell, just 20. And then the Cij value is 280, and we don't have any clue of this, so we cannot find V or this thing. But instead we can go here, which is 480. We know value of U3, so we can find V3. So which means that Cij minus Uij, which is minus of minus 40, which is nothing but 520. So the value of V3 is 520. So once you know the value of V3, and you can easily find U2. So 520, I mean 280 minus 520, which is nothing but Cij minus Vj is equals to Ui. So Ui is here is minus 240. Say here it will become minus 240. It will become minus 240. And this is fairly simple because we know what is U2. So Cij 200 minus this value, right? Say 200 minus 240, just 440. So that will become V4, and actually we have allocated everything, right? So that's basically the stuff we had found out, like U and V, right? So what basically we have done is almost a 50% of all our loops, like we had made imaginary loop using this concept. And finally we will compute this thing, right? So how do we compute this thing is Cij minus the sum of Uij plus Vij. Say Cij minus Uij plus Vij. Say in this case, this is 960 minus 600 and minus 240. When you add it, like it will be some, I'll just explain you, equals to Cij here, which is nothing but 960 minus, we'll have to add these things 600. You can add Vij plus Uij or Uij, I mean Vj plus Ui or Ui plus Vj, does not makes any difference at all, right? So then it becomes 600, right? And that will be the value here. And then say randomly we select this. So what is the value of Cij here is 240 minus sum of Ui, or in this case we'll take this. Last case we have taken Vj plus Ui. In this case we take Ui plus Vj. Then when you talk about that, then that will become 120. So this is an allocation, right? So you might be wondering what the 600, 320, 200, 360 and all, right? So that's a value of the unallocated cell, right? So in a stepping stone method, say the value of D, we have formed a loop and finally we have got something called 200. Whereas in a modified distribution method, by this process, we have got this pretty easily. So say another example, say the value of F, by this loop we got it to be 600, whereas in a modified distribution method we directly got it 600. So that's an power of a modified distribution method. It's very simple and it has more straightforwardness to it. Like the method itself is very straightforward. So in fact you don't make much mistakes in modified distribution method because it does not require any loop at all. And finally it is automatic, it's almost mechanical in terms of working. So if you make this particular uv and u and v elements, then if you do this correctly, then everything will fall in places, right? Something. And then in this case, we take a look at this table. Finally, when all ui and v and all unallocated cell happens, then here it is a 0. So replace 0 with x wherever if it is a 0 value in an unallocated cell. So luckily is only one here. So we'll take it with x. We'll replace 0 with x. So once you replace it with x, then this will become 90 minus x. When you add a value here, so we'll be subtracting it anywhere down there. So it's almost a loop here. So which means we will be taking minus x here. And once you do that, we'll be adding an x and we'll be subtracting an x. And same way, this is what we have got it from stepping stone method in the last iteration, right? So this we got it initially itself. And when you supply 90, x becomes 90, the other value will become 0, this will become 110 and this will become 190. And finally this is what we get it from stepping stone method also, right? And then we'll check whether this is optimal or something. But in this case also, it looks the same, like it will yield the same values as equivalent to a BAM, Vogel's approximation method. Right. Just add this. Like this plus. All right, so we got the same value as equivalent to a VAM or stepping stone method. So which means that this is pretty much an optimal solution, right? So this is a typical example of finding out the optimal solution in a transportation problem, right? So we have come to the end of this lecture.